which is something I have been working a little bit during my my research. And but before that, let me just introduce briefly gamma ray bursts. I guess everybody here knows what they are, but just let me briefly summarize their properties. So they are cosmic gamma ray transients, and with the current facilities like Fermi GBM, we detect almost one per day on average. And with the other main facility, which is the Swift satellite, which has a better localization capabilities, they are less. But anyway, we have a large sample of these, at least for what concerns the gamma ray emission. This gamma ray emission features non-thermal spectra, by which I just mean spectra which are apparently power laws, smoothly connected power laws, and with typical photon energies around hundreds of keV up to tens of MeV, typically. And they have a quite broad duration distribution, which is the one you see in the plot. You see a histogram of the duration distribution of GRBs as seen by the BATSE instrument from the Compton Gamma Ray Observatory, so a past instrument. And at that time, around the 90s, people started to realize that the distribution was bimodal, as you can see also from the plot. And you can set more or less a clear division line at around 2 seconds duration. Below this duration, we have those GRBs which we call short hard, because they are shorter and they also typically feature a harder spectrum, while above we have the long soft GRBs. In the cases in which we can measure a redshift of these sources, we find them to be cosmological, and this also implies very large energies, at least isotropic equivalent energies in their gamma ray emission, which can reach up to few 10 to the 54 ergs, which would mean more than one solar mass converted into radiation if it were isotropic. And the non-thermal spectra, which extends to these high energies, along with the very short variability which is observed in some of these sources, points to a relativistically moving source which moves towards the observer. Otherwise, the source would be too compact to be allowed to be optically thin and emit non-thermal radiation because of photon-photon annihilation and pair production. And so this leads to the idea that the outflows producing gamma ray bursts must be relativistic jets, and their huge energy also points to a very efficient mechanism of production, of conversion of energy, of which the only reasonable candidate is accretion, supercritical accretion onto a compact object, maybe a black hole or a neutron star. All these is corroborated and supported by the association of a number of long gamma ray bursts with supernovae. So we have a number of GRB-associated supernovae, and this leads to the idea that the progenitors of long gamma ray bursts are collapsars, so collapsing massive stars. And these supernovae typically have quite large nickel masses, and they show no hydrogen line. They are type 1 supernovae, and these points to stripped stars, which must have been stripped by their own wind or by binary interaction. We also see observationally.
One question. So when you say large nickel mass, how much large is large?
5 solar masses, something like that. Yes.
Okay. It is a lot.
Yes, it is quite a lot. There are big explosions. Also, the velocities in these supernovae are found to be very large, like 20,000 kilometers per second. So they are quite luminous supernovae. I will show you some light curves in the next slide.
But so I mean, here's from the non-observer point of view. So 5 solar masses of nickel have been observed.
So sorry. I think I was I had some confusion. I mean 5 solar masses of ejecta and around half solar mass of nickel. Yes,
Okay.
10%. 10%.
Okay.
Yes, sorry.
Okay. Thanks.
Thank you. And the host galaxies of these sources are found to be preferentially low metallicity galaxies, young galaxies, often irregular, blue, star-forming galaxies, which is also consistent with the massive star progenitor. And there is evidence for a threshold in metallicity, above which we don't have any long gamma ray burst. And all of these also goes along with the idea that the core of the collapsing star must be rapidly rotating in order for a centrifugally supported disk to form around the compact object which is left as a merger of the supernova explosion. And in this figure, I show a collection of GRB supernova light curve. And here you can also see in gray the values of typical energies, masses, and nickel masses. As you see, is 0.4, no, not 4. Okay, so thank you, Diego, for asking.
You're welcome.
So in this collection, what is striking is that the light curves are all pretty similar to each other, and especially the peak luminosity spans a factor of a few. So this points to very similar progenitors, which produce very similar explosions. On the other hand, if you look at the distribution of energies of GRBs, which in this figure are shown on the y-axis, compared to the distribution of energy in the associated supernovae, the striking aspect is that the energies of GRBs span at least 6 orders of magnitude, whereas the associated supernovae span just 1 or even less. A relatively similar situation, a kind of...
What was the difference between the blue and black dots?
Sorry, yes, the blue ones are collimation corrected.
Okay, they're corrected. Okay.
Yes, but even in that case, they span quite a large range of values, even though they are more uncertain, I would say. Probably more than it is shown in this graph.
Okay, thanks.
For short GRBs, we have a more uncertain, but to some extent similar situation. So it is a long-held prediction that the progenitors of GRBs in general and short GRBs in particular should have been binary compact object mergers involving at least one neutron star. So binary neutron stars or black hole neutron star mergers. But in any case, for a viable central engine to form, so to have a compact object with an accretion disk, you need this kind of system not to undergo prompt collapse or direct plunge. So if there are 2 neutron stars, the total mass of the system must not be above the threshold mass for the direct collapse of the system to a black hole. Otherwise, you would have a black hole remnant, but not an accretion disk around the remnant. And in the case of a black hole neutron star, you need the neutron star to be tidally disrupted before getting inside the innermost stable circular orbit of the black hole. Otherwise, you wouldn't have, again, an accretion disk. On the other hand, in the case of a binary neutron star merger, you also don't want the system to have as a remnant a long-lived neutron star, because newly formed neutron stars that are produced by mergers of binary neutron star mergers are thought to produce massive winds, which would pollute the region surrounding the remnant, preventing the formation of a relativistic jet or its propagation, successful propagation outside of the region surrounding the merger. So these elements suggest that the progenitors of short gamma ray bursts also need to span a quite narrow parameter space in terms of, for example, masses of the components. And another way to look at that is to look at the distribution of luminosities of kilonovae. Kilonovae are something like faint, low mass supernovae. So they are nuclear decay powered transients, but they are produced by the outflows launched after the merger of two neutron stars or of a black hole and a neutron star. And we have only one spectroscopically confirmed and well-observed kilonova, which is AT 2017 GFO, which is the kilonova associated to GW 170817. But there is a number of claims of kilonova signatures in association to some short gamma ray bursts. And some authors, like those shown on the bottom of this slide, tried to collect these observations and tried to construct a luminosity distribution, or in this case, actually a magnitude distribution, absolute magnitude distribution of these sources. And even in the most conservative case, this kind of distribution doesn't span more than just slightly above 2 orders of magnitude. And these must be compared with the luminosity range of short gamma ray bursts, which is at least 4 orders of magnitude. So again, we have that in both cases, we see a very large diversity, at least in terms of energetics in gamma ray bursts, while their progenitors seem not to be as diverse as the GRBs are. So what are the reasons for this? There could be intrinsic reasons. It could be that the central engines differ very much from each other, even though the progenitors don't. For example, we know that the explodability of a massive star is a very complex function of the properties of the star. And we can well have that similar stars which produce possibly similar supernova explosions actually produce either black holes or neutron stars, and these remnants could have a range of spins, for example. Related to these, it could be also that the jet launching mechanism, which produces the jet from the remnant, has a large variability because of a number of possible parameters which can change, which are again the spin or the magnetization of the stellar material or of the merging neutron stars. And it could even be that in some cases we have a very luminous neutrino emission from the inner parts of the disk, which is not the case in other systems because of the differing accretion rates. If the disk mass changes by at least a factor of a few from one system to the other. So we have many intrinsic possibilities. We can even have that the jets are quite similar to each other, but there is some instability which takes place during jet propagation through the progenitor. So for example, the jet propagation through the stellar envelope, which can be triggered or not, depending on some subtle conditions. And on top of that, it could even be that the emission, the dissipation and emission processes that produce the gamma ray emission from the jet, there could be some degree of stochasticity, so that it could be that even though the jets are similar to each other, the stochastic nature of dissipation and emission could produce a varying degree of efficiencies depending on very small displacement on the initial conditions. An attractive alternative possibility, though, is that there are some extrinsic reasons why we see this large diversity in GRBs. It could be, for example, that the surrounding environment plays a role, and we actually do know that for what concerns the gamma ray burst afterglows, which are produced by shocks which take place when the jet material collides with the external medium, so for example with the interstellar medium surrounding the remnant, and depending on the density of the external medium and even on the clumpiness or density profile, it could be that we have diverse properties of the external shock. But even some people have suggested that the prompt emission, so the gamma ray emission, is produced by the interaction of the jet with the external medium. But last but not least, and this is what I will focus on in this talk, is the possibility that there is one leading parameter which drives most of the diversity of GRBs, which is the viewing angle. This is similar to the unification of AGNs first proposed by Uri and Padovani in the 90s. So we know that a large part of the diversity of the appearance of active galactic nuclei is due to the angle under which we observe the source. If we observe active galactic nuclei which have a jet on axis, so if the jets point towards the Earth, we see the blazars, the flat spectrum radio quasars, or the BLAC, depending on some of the intrinsic properties. And then if we observe at larger viewing angles, we can have sources which show the broadline region or don't, or even sources of which part of the emission is obscured by the molecular torus. So in this case, this proposal of the viewing angle as a way to unify these sources was very successful and very powerful, and allowed to narrow down the required range of parameters and of conditions that take place into these sources. So the first time this kind of idea emerged for GRBs also was in the early 2000s. In this slide, you see on the left a figure from a paper by Dale Frail and collaborators, 2001. And on the top histogram, you see the distribution of isotropic equivalent gamma ray energies of gamma ray bursts as measured at that time. They had a few events of which they could measure the redshift thanks to the BEPOSAX satellite. But what they started to realize is that in the cases in which they could measure an opening angle of the jet from the properties of the afterglow emission, and when they used this opening angle of the jet, what is usually indicated as theta jet, as on the right side of this slide, if you correct this isotopic equivalent energy by the collimation, they obtained a clustering. So they found that most of the GRBs had an energy, a collimation-corrected energy, which clustered around 10 to the 51 ergs. And in the same year, Lipunov and collaborator collaborators realized that these could be explained under two competing scenarios. Either you could have that the more energetic jets, which is the case A in this figure, are more collimated, and the less collimated jets sorry. Let me explain that better. Either you have a universal energy reservoir, but you have a differing degree of collimation between different sources, and so you have that the more isotropic, the ones with the larger opening angle, have a lower isotropic equivalent energy content. Or you could also conceive a universal distribution, angular distribution of energy, because since these sources are relativistic, depending on the viewing angle, you would anyway only see the emission from the part of the jet which is pointing towards the observer. And so if you had a universal distribution, angular distribution of the energy in the jet, then the viewing angle could lead to a clustering in the collimation corrected energy, provided that some conditions apply, which are those then spelled out in detail by Rossi, Lazzati, and Rees in 2002. So let me again summarize. The idea is you can have an angular distribution of radiated energy per unit solid angle. So it is this function epsilon of theta, which is the energy per unit solid angle radiated by the jet, and this theta angle is measured from the jet axis out. And if the source is highly relativistic, then the isotropic equivalent energy that you would see at a viewing angle theta view is just 4 pi the radiated energy per unit solid angle at that angle, because you only see the part of the jet which points towards the observer. If the duration of the jet activity is independent of the viewing angle, then the same applies to the luminosity. The luminosity has the same angular dependence. And in this paper, Rossi and collaborators found out that the off-axis afterglow light curves of jets which have an angular distribution of energy which goes as the angle to the -2 produce breaks in the afterglows which look like jet breaks, which are the features that are used to measure the opening angle of the jet, with the same dependence on the viewing angle as it was the dependence on the opening angle in on-axis uniform jets. So these would explain why you see a clustering of the energy when you try to collimation correct these isotropic equivalent energies. It is just a kind of a cancellation, okay? And this kind of distribution of energy in the jet with a theta to the -2 distribution was even justified on theoretical grounds by Lazzati and Bigelman 2005, based on the propagation and the dynamics of the jet breakout from the progenitor stellar envelope. But what we found in 2015 in this paper led by my colleague Pescalli is that this kind of angular dependence of the luminosity, so if we attribute to the jet an angular dependence of the luminosity like theta to the -2, then we don't reproduce the observed luminosity function of long GRBs. To reproduce it, assuming that all jets have the same properties and they are just seen at different viewing angles, you need a much steeper dependence of the luminosity on the viewing angle. Okay. And in a companion paper led by myself, we also showed that the dependence of the isotropic equivalent energy as seen by an observer at a certain viewing angle does not necessarily follow exactly the distribution of the radiated energy, because in the case in which you have a varying Lorentz factor, the varying relativistic beaming as a function of the angle from the jet axis leads to some effects. So leads to the fact that depending on the viewing angle, you can be dominated by different parts of the jet, not necessarily the part of the jet which is pointing towards the observer. And in general, you must perform an integral over the jet surface, taking into account for the relativistic beaming. And what you get is that even in the case of a uniform distribution of energy per unit solid angle, like the one which is shown in this figure in gray and blue, you have that off-axis you have a smooth decay of the observed isotopic equivalent energy. But in the case of a decaying radiated energy, in this case it is a Gaussian, and also a decaying Lorentz factor, then the outer parts of the jet contribute much more to the emission as seen by off-axis observers, and the decay is much smoother. And in general, even for a Gaussian distribution, so a very sharp distribution of energy per unit solid angle in the jet, you have a power law dependence of the isotopic equivalent energy with the viewing angle. And using this fact...
I'm sorry, I have another question. So in your previous model, how would the cocoon affect your isotropic energy?
So in this case, it is just you define some phenomenological functions which define how much energy is radiated per unit solid angle at any angle, and you don't bother about what is it really. So if it is the jet, the cocoon, the interface, or all these things that now are quite fashionable and all the people are talking about. At that time, actually, there was not much talking about the cocoon, and we were just, assuming that you have some angular distribution, because in the end you must have some, right? A Gaussian is probably the most natural, realistic representation of something which is very sharp, right? Mm-hmm. So even a very sharp distribution like a Gaussian anyway leads to some to an apparent dependence of the isotropic equivalent energy with the viewing angle, which is not exactly the same as the intrinsic one.
Actually, here, Fabio and his student Gerardo Urrutia are actually doing that. So maybe you can later also talk about that.
Yes, absolutely. I would like to. So at that time, what we showed...
I have a question too. So what is the relation between the prompt emission and the afterglow emission? When you have a lower energy in the prompt, you get a lower energy in the afterglow, or not? Because if it's, I mean, there should be this relation, no? If it's...
So in this setting, it can be anything. I will discuss that. I will discuss that.
Okay.
Well, observationally, you have quite a correlation between the prompt emission energy and the energy you find in the afterglow, even though the energy in the afterglow is not an easy thing to measure because of many degeneracies in the modeling.
Yeah.
And so for quite a long time, people believed that the efficiency of the prompt emission was extremely high, and that 90% of the energy of the jet was released into the prompt emission, and then just 10% remained for the afterglow. But this is based on the afterglow modeling, and it was actually hampered by some prejudice on some of the parameters. And then more recently, people are more inclined to believe that the efficiency is around 10%, but still quite similar from one jet to the other, which should mean that the distribution of energy in the jet at the time of the afterglow is the same as that you see in the prompt emission. But I would argue that this is probably most likely not the case, actually. Most likely you have an angular distribution of the efficiency as well.
Okay.
But let me go back to this like historical reconstruction. So at that time, we showed that with a Gaussian structure, with a Gaussian dependence of both the radiated energy and the Lorentz factor with the angle from the jet axis, you could reproduce the long GRB luminosity function very well, actually, with a quasi-universal structure, which means a structure which is very similar among different jets, with just a small dispersion of the parameters. For example, half an order of magnitude of dispersion in the core energy of the jet, and obviously assuming an isotropic population of jets. And we even had a nice side effect, which was if you assume that the comoving spectrum is the same at any point in the jet, and then you take into account the relativistic beaming and how the observer sees this emitted spectrum, then you have that the distribution of the sources in the plane isotopic equivalent energy and peak photon energy of the spectrum follows a well-defined correlation, which does reproduce the observed Amati correlation. So the correlation that is found between these two quantities observationally in long GRBs and hinted at also in short GRBs. So we were very happy because we had also this way of explaining this correlation as due to a sequence of viewing angles with some dispersion due to the intrinsic dispersion of the properties of these sources. So then one can be happy that there is probably, maybe, possibly a way to unify these sources by assuming a jet structure. But then one must explain where the jet structure comes from. Naturally, if you could measure the distribution of energy that comes out from the central engine, either a spinning black hole from which the energy is extracted by a magneto-hydrodynamical mechanism such as the Blenford-Snellick mechanism, or if it is neutrino, antineutrino annihilation from neutrinos emitted by the inner disk in the funnel above or below the black hole, or even if you have a magnetar wind as the primary source of energy for the jet, in any case, you would have an angular distribution of energy that's natural. You cannot have a process which produces a sharp jet, right? So it is obvious that you have some. But we have a possibility that actually what really shapes the jet structure is its interaction with the ambient medium, either the stellar envelope or the kilonova ejecta. And so last year, myself and some collaborators tried to develop a semi-analytical model of this kind of interaction, which had the goal of trying to predict the final structure of the jet after the breakout based on the parameters of the jet at launch. It is an hydrodynamic model, so we do not take into account the effects of the magnetic field, and we assume the jet stability, and we parameterized the way the energy is spread angularly after the breakout of the jet. And so the idea is actually well known in the literature. So you have that the jet is produced by the central engine, but it collides with the ambient medium, which is for example, the stellar envelope, and it produces a forward and a reverse shock, and the region between these two shocks is called the jet head. And typically, this jet head has a bow shock as a forward shock, which means that part of the material which is shocked within the head is cast aside and occupies a region surrounding the jet, which is called a cocoon. And this region is overpressured with respect to the ambient medium, and it could be also overpressured with respect to the jet. So the pressure of the cocoon indeed can balance out the transverse momentum of the jet material and collimate the jet. And so you have the self-collimation of the jet as it propagates inside the stellar material or the kilonova ejecta. And then at some point, the jet and the cocoon reach the border, the external border of the envelope, and then they break out. At this time, you have some pressure in the cocoon, which is the pressure at the breakout. But as soon as the cocoon reaches the outer part of the envelope, you have a blowout of the material because there is no confinement anymore, and so there is a pressure loss. After a delay, which is given by the time it takes for sound waves to get from the surface down to the collimation height, you then have a collimation loss in the jet. And then you have, at some point, that the injection of the jet, the production of the jet stops. And in the meanwhile, you have the blowout of both the jet, which is losing collimation, and of the cocoon. And then at some point, all the material has been blown out, and it is moving initially maybe not at a highly relativistic speed, but then it accelerates and it becomes highly relativistic. And all this material will have an angular distribution of energy, which is the result of all this interaction. And due to the entrainment of the material of the jet with that of the cocoon, you have an interface, you have some mixing, and then you have a kind of a smoothing of this structure during this process. And this is basically the ideas behind the model. And this reproduces quite well what is found in numerical simulations like these from Gottlieb and Nakar 2018. And in this slide, I show you some of the jet structures which are obtained from numerical simulations by two different groups. One is from Davide Lazzati and collaborators 2017, and one is the McFadyen group. And these are two-dimensional simulations, hydrodynamical. And the model does reproduce quite well the angular distribution of energy, and decently the distribution of the Lorentz factor, the average Lorentz factor of the material in the jet after breakout. And so this is to some extent successful in reproducing a selected number of simulations, those which we had enough information on to be able to try to reproduce them. And so what we try to do is to then assume some density profile of the progenitor, to take a progenitor model. And in this case, we took the usual pre-supernova low metallicity rotating massive star model from Woosley and Hager, the 16 Ti, which is the one which is most widely used as paradigm of the progenitor of long GRBs. And then we injected our jet, let's say, so we rerun our semi-analytic code on this progenitor, but we did that for a distribution of initial conditions of the jet. We took a log normal distribution of luminosities, kinetic luminosities of the jet at its base, with an average of 3 times 10 to the 49 ergs per second and a less than 1 order of magnitude in dispersion, a log normal duration distribution, the duration of the jet production, and a fixed opening angle at the base. And then we ran the simulation. And what we found, obviously, since the properties of the jet are very similar to each other at launch, then also the jet structures that we get are very similar at breakout, also because the progenitors are all the same, with some distribution. So here you see the distribution of the energy per unit solid angle in the jet and the average Lorentz factor in the jet material, and also in the cocoon, which is the wider part, which is shown in the bottom right of the leftmost figure. And as you see, you have some wider cases, but most of them are quite narrow, just 1 or 2 degrees, with a very large cocoon, but which features a very low energy per unit solid angle when compared to the jet.
Sorry, and what launching radius and what launching Lorentz factor did you use?
The launching radius was, if I'm not mistaken, 3 times 10 to the 6 centimeters, or 10 to the 7, something like that. And the initial Lorentz factor is 100. So it is assumed to be relativistic at all times, the free expanding jet, and then obviously the propagation, then it is slowed down by the interaction with the envelope.
Okay.
So this is the resulting distribution of structures. So in this case, we have a quasi-universal structure distribution, but it is obtained from the modeling, from the, let's say, physical modeling of the interaction with the progenitor. And here the assumption is that the memory about the initial structure at launch is lost, and it is what dominates what determines the structure at breakout is actually the interaction with the progenitor. And what is very nice is that when you then assume a constant efficiency at any angle for these jets, and you compute the distribution of luminosity of this population, this synthetic population of jets, then it reproduces strikingly well the luminosity function of long GRBs, the observed luminosity function. And there are some indications that something weird is taking place, because as you see, for example, if you look at jets which have a 10 to the 52 isotropic equivalent luminosity, they are observed at more than 5 degrees, which is most likely too much. But anyway, what is nice is that the shape is reproduced very well with these parameters, with these initial guesses. And what about short GRBs? Here, the luminosity function is more uncertain, but we do have observational evidence for the jet structure, because we have the observations of GW170817 and the associated GRB, which was shown to be compatible with, to be explained, well explained by a quite sharp power law or even Gaussian energy distribution, which had to be invoked to explain the initial shallow rise of the light curve, as observed in the radio and then also in the optical and X-rays. And in this slide, you see the distribution of energy and also Lorentz factor in the jet of GRB 170817A, so the jet associated to GW 170817, as obtained in a paper by Giancarlo Ghirlanda, myself, and collaborators, 2019, where we also constrained the structure by using information from the VLBI centroid motion. And we also contribute in supporting the idea that this was indeed a successful jet by measuring the size of the source in the VLBI images and finding that it is too compact to be an isotropic outflow. And so here in red, you see the structure of the jet as found by our modeling, with the pink region representing the uncertainty on the structure. And here, the same structure is shown by black lines, and the structures that result from the same approach as before, but applied to the short GRB case from the jet propagation model, are shown in red and orange and yellow. In this case, we assume the same kilonova density and velocity distribution as in the paper by Xie that I mentioned before, and in the same also by Kaslival and Gottlieb. And then we use similar distributions of the jet properties at launch, except for the duration, which is shorter. And then we obtain this distribution of structures, which are quite compatible with the structure that we see actually in GRB 170817. And also in this case, this can be used to reproduce the luminosity function, even though it is not too much informative, because the uncertainty in the luminosity function is quite large. But the results are more similar to the Vanderman and Piran luminosity function than to that found by Ghirlanda and myself in 2016. Sorry, I forgot to put the slide in, then I can show you the resulting luminosity function afterwards. The idea that the jet structure of short gamma ray burst could be quasi-universal can also be supported in a completely different way, more observationally based, which is what we showed in this paper from 2019, led by myself. So what we showed is that if you take the structure that I showed you before, the GRB 170817 structure that we find from the modeling of the afterglow and the VLBI motion, and then we ask ourselves, what should we see as an afterglow when we see this jet on axis and at the typical distance of short GRBs and with the typical ISM density which is found for short GRBs, and then the result is the black line when you see it on axis. So it is essentially perfectly in the middle of the observed population, which is shown by the colored lines on the background. So the colored lines on the background are the X-ray afterglows as collected by Fong 2015. And in the smaller panels, you also have the radio and optical observations of the same sample of short GRBs. And in black, you have the predicted afterglow emission for a jet with the same structure of 1708, 17A, but seen on axis and placed at a typical distance of short gamma ray bursts. In orange, you have the off-axis case, which should reproduce instead the original viewing angle of 1708, 17A. On the right figure, you have essentially the same approach applied to the prompt emission. So in this case, again, we assume a constant efficiency as a function of the viewing angle, of the angle from the jet axis, and we predict the isotropic equivalent energy versus the peak energy of the spectrum as a function of the viewing angle, and they make up this line, which is the same as the Amati correlation that I was talking about before. And then you have a sample of short GRBs with measured redshift in black, and as you see, the median of the distribution. So in this case, you have a distribution of relations between AISO and the peak because there is uncertainty in the jet structure of GRB 1708, 17A. But anyway, the median is compatible at 1 sigma with most of the I observed isotopic equivalent energies and peak energies in short GRBs, with a very nice and a funny exception, which is GRB 1708, 17A. So essentially, you cannot actually explain it by invoking the same structure as that you use to model the afterglow and a constant efficiency and an identical comoving spectrum at all angles. You can, if you assume that the comoving spectrum changes, or probably also if you assume that the efficiency is a function of the angle. But anyway, this is another indication that you can possibly interpret most of short gamma ray bursts as being produced by similar jets but observed at slightly different angles. So there are obviously some missing pieces in all this unification work. So for example, one should demonstrate that all GRB observations can be explained by a quasi-universal structure jet. So one should be able to demonstrate that one can reproduce both prompt emission and afterglow of all the jets that we could observe until now with a consistent structure with only a small narrow variability in the parameters. Yeah. Also, one thing which should be investigated more is what do jet breaks tell us in the quasi-universal structure jet scenario. In some slides before, I told you that in 2002, Rossi and collaborators found that the jet break time in off-axis structure jet afterglow light years scales as the viewing angle squared, but this is oversimplified and should be looked at in more detail, because these should give us the reason why we find similar collimation corrected energies when we model all jets as on-axis uniform jets. Also, we need to work out in a physical way how do the dissipation and emission mechanism depend on the angle. So do we have a dependency of the efficiency of prompt emission with the angle? Do we have differing emission mechanism, dominating emission mechanisms at differing angles? For example, we could have that the shock breakout dominates at larger angles over the emission from the prompt emission from the jet, which could be, for example, the case in GRB 1708-17A, and this is what is advocated actually by, for example, the Israeli group. And how relevant is the cocoon emission? Does the cocoon emit thermal radiation? Does it emit non-thermal radiation? Does it have an important shock breakout? So all of these has to be worked out in detail and is still missing. And obviously, so the jet propagation model and the structure formation model that I described before is absolutely oversimplified. One must work out the role of the magnetic field and also the role of possible instabilities, both magnetohydrodynamical and also hydrodynamical in shaping the jet structure. And there is some work about these, some recent work by Ore Gottlieb, and also see an important piece of work by Bromberg and Chekhov 2016 about the role of the magnetic field in structure formation. And on top of that, we also really don't know how diverse actually are the progenitors. In the examples that I showed you, the progenitors were assumed to be identical to each other, but we obviously have some degree of variability between the progenitors. And for example, for short GRBs, we could have that black hole neutron star mergers are could play a role in the population, and so probably the jets produced by these kind of systems are intrinsically different from those which are produced by the binary neutron star mergers. And for long GRBs, you could have, for example, POP3 stars as progenitors, and these are obviously very different from these typical Wolf-Rayet highly rotating star as the usually assumed progenitor of long GRBs. So let me just make some final remarks. So it is possible that we could unify gamma ray bursts under the quasi-universal structure jet scenario, but it is still a long way, still a lot of open questions. And anyway, quasi-universal means that you have intrinsic variability, some degree of it. So this has anyway some impact, for example, on the possibility of using gamma ray bursts for cosmography. So if they had exactly the same structure, then you could figure out if you had an independent measurement of the redshift, you could figure out the viewing angle, or if you had an independent measurement of the viewing angle, you could figure out the redshift. But this is not the case in a quasi-universal scenario in which you anyway have some intrinsic variability. And gravitational wave observations, especially in the third generation gravitational wave detector era, will help a lot because they can provide information, independent information about the progenitors of short gamma ray bursts, but less so for long gamma ray bursts because collapsing stars can be seen in gravitational waves only very, very close by. And anyway, other extrinsic variables remain. But I think it is anyway a very exciting prospect to try to work on this unification, and I'm very happy that many people are now taking seriously the possibility of a jet structure, because at the time when I started working on these, we were almost the outcasts of the community, and everybody just considered the uniform jet scenario. And while now the jet structure is omnipresent and everybody is working on it, and I think these are good step forward of the community. So thank you.
Thank you. Then we can start with the questions. Fabio, please.
Yeah, also Diego says that he has a lot of questions. So I have a few questions too. Well, thank you for the talk. It was very interesting. The first one, when you were talking about the Frail, the two scenarios coming out from the Frail paper, the 2001 paper, 2000, something like that.
Yes.
So how could you distinguish between the two observationally? Is there a way to distinguish? How can you say this one is correct and the other one no?
Well,
the following
it is clearly not an easy question. So I think one point is that you anyway need some degree of jet structure, because it is just not natural to have a sharp edge in the jet. But the observed clustering in the energies, when you collimation correct them, could not be the result from this. Actually, what one must take into account is that actually this clustering nowadays is much less narrow. So it was more a coincidence, let's say. So now if you collimation correct the energies of jets for which you have an estimate of the opening angle in the uniform jet scenario, then you get anyway some orders of magnitude spread. But I would say the way to distinguish the two scenarios is just to have ways to derive the structure of the jet from observations, which is both work on the population and on a work on single cases, for which you can demonstrate that a structured jet scenario explains better the observations.
So how do you get the jet structure in the 1708, 17A? Because I mean, it's very degenerate. The parameter space is very degenerate, no?
Yes, what breaks the degeneracy is really the VLBI centroid motion, I would say. This was also shown by other groups recently. So basically, yes, if you only have the light curves, you have a whole lot of parameters which can give you the correct light curves. But if you need to also reproduce the observed centroid motion from the VLBI, then these sets quite narrows down much more the allowed values, especially of the ratio of the energy in the jet over the density and also of the viewing angle. And so by narrowing down these degeneracies, then you have that they are also reduced, that the uncertainty is also reduced on the other quantities. Okay. But still you have, I mean, for example, here we are assuming that the jet has a power law structure, and you can try to do the same with another assumption on the structure, and you can get equally good answers, for example, with a Gaussian jet. Okay. And many other groups show that you can reproduce the emission with other structures. But I would say the basic properties are quite settled. I can show you this figure. The panel on the left, this is from another paper by myself from this year. The left figure shows the distribution of kinetic energies in the jet as derived from jet structures from different groups. And as you say, they all cluster in the end around the same value with a spread of essentially one order of magnitude.
Yeah, so it's 10 to 50 mass plus minus 1, right? From 10
something
to
like that.
9
Yes,
to 10 to 51. Yeah, but it's a huge
Well, it is definitely not 6 orders of magnitude as the isotopic equivalent energy is observed, right?
Okay. And what about the low luminosity GRBs? Are they? How do they fit in your universal structures, or they are just off-axis GRBs?
Yes, as I said, so in the most simplified scenario, they must be off-axis because it is the only leading parameter, right? Then, if you allow for some variability in the intrinsic properties, then you can have that some are off-axis, but others are not, and this clearly makes the question more complicated. I think most low luminosity GRBs do have some signatures which can be compatible with an off-axis interpretation. For example, there is a clear correlation with the variability between the variability and the luminosity. So lower luminosity events have also a very much less variable light curve, and these can be explained as due to a viewing angle. But this is only qualitative anyway.
Yeah, so the last one. So if you look at the distribution of nickel masses.
Round those, Fabio.
Okay. I will ask. Well, okay, later. Thank you.
Okay.
Gerardo, please.
Yes, can you hear me?
Yes, I can.
Thank you for the talk. And I have a question about the final structure that you showed in, I don't remember the slide, and the final calculus of the structure before the breakout. Sorry, after the breakout.
Okay, you mean here?
Yes. What about the free expansion? You mentioned that evidently the information of initial conditions are delayed. And what about the free expansion?
Yes, I agree that you can have a rearrangement of the structure also due to the free expansion. This, to some extent, factored in the model by the phenomenological way we smooth out the structure at the end. Okay, so this could be a way to take into account the free expansion phase, which can produce some rearrangement of the structure. But anyway, people seem to find that the structure is quite frozen after a short time after the breakout.
Okay.
But I think this is difficult anyway to investigate, especially in simulations, because this is something which happens at over orders of magnitude scales. So probably this is a very important question which must be answered in much more detail in the future.
Okay, and some people when the and in many works of structure jets, some people assume that the function, the analytical function, which depends the theta angle, has the same structure for the energy and the Lorentz factor.
Yes, there is no reason for that. Yes, I think it's just a matter of simplicity. Well, you can actually conceive that there is some relation, because in the end, the Lorentz factor, you can see it as the ratio between the energy and the mass that is present in that part of the outflow. So it could be that the processes that redistribute energy are similar to those which redistribute mass, and so you would have that the dependency has the same functional form, but it is not granted anyway.
Yeah, could you change the function of the Lorentz factor?
Yes, obviously you could do that. You could do that. Well, as you see from our modeling, actually the dependence of the Lorentz factor and that of the energy are quite different in the end, especially in the short GRB case. Well, no, they are not that much. But in this case, this is semi-analytical, and there is no analytical function describing the structure. But anyway, yes, they look quite similar in the end.
Thank you.
But there is no precise reason for that, and it could be that it is not the case. Also, I think one oversimplification which is present everywhere is that we are attributing just one Lorentz factor to every point, angular point in the jet, while we will certainly have a distribution of Lorentz factors at any point of the jet. And this could also lead to some observational effects. For example, it could be that the reverse shock has very different properties depending on the angle at which you are observing it. The reverse shock which takes place at the time when the jet starts to decelerate in the interstellar medium, I mean.
Okay.
Well, it's my turn. Thank you for your talk. It was very good. My question, maybe silly, is related with the fact that your models can reproduce almost any light curve. But if we see the problem from the other side, do you think it's possible to predict a structure? I mean, why we have not seen another GRB of axis yet?
So I think part of the answer resides already in the work by Rossi and Lazzati 2002. So in this slide, I show a figure from this paper, which is a very old one, where they already started to compute structure jet of axis afterglow light curves. And as you see, they really look like on-axis jet light curves. So the problem is that the behavior of on-axis uniform jet light curves is quite diverse, and the diversity that you have in off-axis structure jet cases does not have enough definite and evident differences which can be used to definitely point out that this case must be an off-axis jet. The only exception is GRB 1708-17A, in which case we were observing sufficiently off-axis as to be dominated by the emission of the wings of the outer part of the structure. But I would say this will never be the case for cosmological GRB. They anyway must be quite on axis for the prompt emission to be observed. Probably in the future, if we will be able to have gravitational wave triggers for some of these GRBs, we could be probably able to see them as orphan afterglows without a GRB, a gamma ray burst trigger, but with a gravitational wave trigger. Or possibly we could even conceive of discovering orphan off-axis afterglows from optical surveys, in which case, if we recognize them and if we monitor them, we could be able to find clear signatures of a jet structure. But I would say it is anyway a very difficult problem because of the many degeneracies in the afterglow modeling and the diverse behavior of the afterglow light years. And also another problem is that actually the standard afterglow scenario does not completely reproduce all GRB light years as we see them. We have plateaus, steep decays, and flares, and strange slopes which don't satisfy the closure relations. And so all of this means that there is a high degree of diversity, but also means that it is difficult to explain it with a model which has more parameters, because already the basic model has many and has a lot of diversity, but it anyway cannot reproduce all the features, and probably some of these features are just not consistent with the standard scenario. I don't know if I explained it.
Yes, perfectly. Yes, I see your point. Thank you very much.
Thank you.
Diego, please.
Yeah. Hi, So,
Hi.
I mean, I guess the vast majority of the GRB community would agree that either long or short, it's always a collimated relativistic jet fighting versus the medium that's surrounding it. Either if it's the collapsar material that's on top of it, or if it's the material that was launched during the neutron star merger. So I see that as a universal, like everyone would agree on that. What I still don't understand is where is the quasi-universal of your model? Is it that you're just saying that the jet is Gaussian, or that it's only the angular distribution? And also, like what you're showing, everyone now is gonna at least accept that it's a jet and a cocoon, and it depends on the cocoon is formed depending on the ramp pressure of the jet and depending on how much material it's going through. So
yes. So I would say, well, the cocoon is something which comes out from the computation. So
naturally,
if you use the same model and you have a very low density environment, then there is no cocoon, and that's it. But for typical properties, at least the properties that we expect for the progenitors, then you expect also the cocoon to form and to also collimate the jet.
Mm-hmm.
And this was already shown by many,
including
I think some paper in which you were co-author. And so in my oversimplified work from 2020, the quasi-universal nature of the structure comes because I have a distribution of properties of the jet at launch.
Okay.
They are quite narrowly distributed, and there is no reason why the jets have these distributions. They are just assumed distribution. But the result is that obviously you have a quasi-universal distribution of properties at the breakout. So the idea was just that if the structure is produced by the interaction of the jet with the progenitor, then a small diversity in the jet or in the progenitor, which is to some extent the same, will produce some diversity in the structures that you see, which could be enough to justify the intrinsic variability that you need for the quasi-universal structure jet scenario to work. Okay. Because you anyway need some variability. Okay. But then you must explain why they are diverse, and this again must be something related to the properties of the central engine. So
so you don't care in your model what the central engine is. Is it the magnetar? Is it the black hole? Is it?
Exactly. In this case, I don't care. I mean, I do care absolutely, and I would really like to answer. And there has been a recent work by myself and Bruno Giacomazzo where we try to answer the question whether in GW17 or 17 the jet launching mechanism was Blandford-Znajek or the anti-neutrino annihilation. But at least in this case, with the data we have, we cannot conclusively answer the question. And okay. So it could be anything.
Okay. I'll wait for round 2 for my other questions.
Fabio?
Yeah, my other question was about the nickel. No? So there is a distribution of nickel mass produced in supernovae associated to gamma ray burst. So the distribution of nickel mass seems to indicate that or the progenitor is different, or the energy injected in the progenitor star is quite different, because it's a large spread, no? Can be from, I don't know, 0.1 to 0.5 or more solar masses of nickel. So,
do you call this a large spread? Okay, sorry, I'm not completely expert.
Okay, depends on, yeah.
I would say this is quite a narrow range, especially if you compare it with the whole population of supernovae, right?
Yeah, that's true. But on the other side, I mean, that indicates that you have different progenitors, or
Yes.
different
Clearly.
properties for the jet. So how can you, in that case, justify to have the same outcome for the jet? And also in a similar direction, no? In long versus short, and you actually mentioned that, that probably short have different intrinsic distribution. The environment is very different, no? So
Yes. In the model, we do have a different environment. We do have a kilonova ejecta model for the environment in the short gamma ray burst scenario. So as I said, the idea of this unification is to have not a universal structure, but similar structures among different jets with some variability, which could be either attributed to the diversity in progenitors or to the diversity in jets, but most likely on both, right? So you will certainly have a range of masses of the progenitor stars, a range of spins, a range of metallicities, and maybe some are in binary and some are single stars. And so I think that there is anyway some possibility for the properties of the progenitor and of the jet to vary. And in the simple model I was talking about, this is just represented by the distribution, the spread in the properties of the jet at launch. This should, to some extent, account for the diversity of both the progenitor and the jet, since anyway the interaction depends, let's say, on the ratio of the densities and mass energy and something like that. For short gamma ray bursts, again, you can have that there is some variability. You need actually to be some variability there. We know, for example, that the binary neutron stars in our galaxy do have a distribution of masses, and even if it is quite narrow, we actually expect them to, once they will merge in the faraway future, to possibly give rise to different remnants, even with this small variability in the masses. And so, I mean, I think the takeaway point is probably the viewing angle is important, does determine to some extent the variability, and it could be the leading parameter explaining the huge distribution of energies that we see. But it is not the only one for sure.
Okay, thank you. And another one, following what Rosa was asking you, no? So there were two orphan afterglows observed by ZTF, both on axis. I mean, they didn't observe the gamma emission,
Yes.
they just observed the optical emission, and after, yeah. So where are the orphan off-axis afterglows?
Yes. Well.
Why are they not observed yet?
So I think so. There has been a work about this led by Giancarlo Ghirlanda in 2015, I think.
Okay.
And so I would say the rates are not unexpected. So it is not unexpected that we don't see orphan afterglows with the facilities we do have now. If after 1 year of LSST there will be no orphan afterglows, then we can come back and discuss and find out why this is the case, because it would be anyway surprising even for the uniform jet scenario, right?
So if you see Giancarlo's paper, the prediction were 20 off-axis GRBs per year by ZTF. And we are now at 0, no? And 50 by LSST.
Probably he was optimistic about ZTF.
Okay. Thank you very much.
Thank you. Yeah, sorry, I didn't remember the point about ZTF. I think a very big issue with these sources is that it is not easy to recognize them. I mean,
yeah, that's true.
Even if you see one, how do you really know that this is an off-axis gamma ray burst? And even in the two cases seen by ZTF, how do you know that you are not seeing slightly off axis the jet? I mean, you really need very good early data to be able to exclude small viewing angles, right?
Yeah. Yeah, it can be. I mean, but in the jet, less than 10 degrees, 15 degrees, something like that. No, the last one, the one that was last
Yes.
week or 2 weeks ago, something like that.
Yes.
But not 50 degrees.
Yes. Well, I would say it's not surprising anyway, because the D-beaming is very strong also for the afterglow. So
Yeah, that's true.
they get faint very fast, as you know.
Yeah. Thank you.
Thank you.
Diego?
I don't know if someone wants to ask before, so that it's not just Fabio and me versus On.
Leo?
Not yet.
Okay. So I'll ask a quick question. So at the end of your talk, then you were mentioning that magnetic fields should well, they can modify and give variability, but where do you think that the magnetic field, like the magnetic field of the jet or the magnetic field of the ambient medium, or both, or?
So I think most people in the GRB community would bet that the launching mechanism is Blanford-Znaeck, and in that case, the jet material at launch is highly magnetized. So if you don't have a way of getting rid of this magnetic field, then the jet will be magnetized all the way up to breakout. And it has been shown by many, actually, that this has an effect on the structure, because, for example, it prevents the mixing between the cocoon and the jet, and also it changes the conditions for both the propagation and the collimation. And so it could be that jets are highly magnetized and they keep their magnetization up to the breakout. There are actually indications of the contrary, and this is explained well, I think, in this paper by Bromberg and Chekoskoy. So actually, it was already understood before by by Bigelman and collaborators. Actually, you have, during the propagation of the jet, the conditions for the kink instability, global kink instability to take place, and these could dissipate most of the magnetic field of the jet during propagation. And so the jet could actually get to break out being not highly magnetized. And so it could be that it is not extremely important, but again, you can see these recent papers by Ore Gottlieb, where he uses a equipartition magnetization, so not a magnetically dominated jet, and he shows that you have quite some difference in the resulting structure.
Okay.
Even though we all know that these simulations are more difficult than the hydrodynamic ones. Yeah. Some indications that you don't have an extremely high magnetization are seen in those events where you can see a reverse shock at the beginning of the afterglow. And for a luminous reverse shock to take place, you cannot have a high magnetization in the jet. So this could be an indication that indeed the jet at some point gets rid of its magnetic field, if it has any, when it's launched, or that the launching mechanism is not Blanford-Znaeck.
Okay. And nearly last one of this round. So can you put your figure where you have your yellow, orange? So I didn't quite follow.
This one?
So, well, then you had some that said this work, and then Lazzati and she.
Oh, sorry.
So what I didn't know is, no, then the other. Sorry. So is this for the analytic model, or this is taking into account the hydro simulations?
So the model is, let's say, analytic or semi-analytic, and it is validated by comparing it to these 3 hydro simulations.
Okay. And then how do you obtain the next curve? The yellow.
Then we obtain these by the semi-analytic code. So there is no hydro simulation here. It's just analytic formulas and integrals which are solved numerically. And we get, this is the distribution of structures. So the red line is just the median of the distributions. So I'm not showing the individual jet structures that I get from this series of computations, but these are the initial conditions, the distribution of initial conditions. So I have, it was 1,000 jets with varying luminosity. This is a histogram of the luminosities, and varying durations, and with this opening angle at launch. And then this progenitor, the same for everybody. I just need the density profile because it's hydro. And then this is the resulting distribution of structures. So we have some which is like something like this, which is wide and flat, but it's just rare. Most of them are close to the red line.
Okay, gotcha.
50% is contained in the orange area, and the same for the Lorentz factor.
1,000 different models in this issue.
Yes, this is I think 1,000. Yes, and the same for the short GRBs.
Okay. Thank you.
Thank you.
Is there more questions? Diego or Fabio?
No.
Then I have one last one that I didn't quite also. And also in your analytic model, when you put just when the jet has broken out, when you have that series of nice, exacto, like that. So what I don't understand is why the jet, when it breaks out, doesn't it also expand like the cocoon? You're putting like if the jet collimates once it's outside, but there's no pressure pushing it. So why is it collimating?
Well, when you break out, if you are collimated at breakout, then you can lose to some degree the collimation, but not that much, because even if you expand at speed of light in the co-moving frame, there is not much time in the lab frame for the lateral expansion to take place. And in the end, if you do the computation, you have that the angle that you can, the maximum angle you can get to with the lateral expansion is 1/gamma. So if 1/gamma is smaller than the opening angle at breakout, then you just don't expand laterally.
So you're saying it's still relativistic beaming?
Not beaming, but the relativistic dynamics, yes.
Vale, that's all for me.
Okay, well, if there are no more questions, one more time, thank you all. I think you are a great speaker, and then maybe when the lockdown finish, you could come and visit us in Mexico. We'll be very glad to receive you and share some projects with you.
Thank you so much, Rosa. I would be really, really glad, and I'm really looking forward to that.
Well, we'll see how we bring you on.
Sorry?
We'll see how we bring you.
Ah, yes.
Oh, okay, yes.
Well, thank you very much. Please turn on your camera to say goodbye.
Yes.
Bye.
Bye, everybody. Thank you.
Thank you. Goodbye.
Thank you. Very nice. Thank you.
It was a
Bye.
pleasure, a honor to talk to
Bye.
you, and see you soon.
Bye.
All the best.
Bye.
Stay safe and sound. Ciao.
Thank you.
Thank you.
Yes, you too. Bye-bye.
Pues se están yendo todos.
Sí.
Diego, adiós.
Adiós, se fue. Entonces como quieras, Fabio.
¿Cómo?
No,
¿Quieres decir algo?
tú ahora eres el jefe.
Pues nada, es que no sé si... ¿Pero dónde estoy yo? Ah, no, mi cara no está.
Esto se va a grabar también.
Si quieres paramos. Déjame paro la grabación. Ya, se acabó.